Hey, good morning. Glad to be here with you. My name is McGinley, and today I'm going to be talking about the effect of Industry 4.0 on industrial control system security architectures. Now, some of you might already be familiar with industrial control system, and some of you may have no idea of the concept whatsoever. So regardless of your experience, I'm hoping you can learn something from this talk. Let's get started. So first of all, we're going to explore the security issues in ICS and what makes them different from IT systems in these regards, looking at architectures such as the Purdue model, which you can see on the right of the screen there. And we'll also examine proposed solutions to creating secure architecture for Industry 4.0 and Industrial Internet of Things technology. Before we get started, just a quick overview about myself. I'm Michael McGinley. I'm a cybersecurity analyst. I studied at Glasgow University for 5 years and gained my master's in computing science last year. And in my final year is when I developed a keen interest in industrial control systems, and particularly the security of these, which is somewhat of a niche part of cybersecurity, or at least it used to be. When a lot of people think about cybersecurity, they tend to think more about personal computers, financial crime, data loss. But in recent years, there have been a number of high-profile security incidents in the industrial sector. Such incidents have the potential to be catastrophic. And when you think about the criticality of industrial networks and the systems which are connected to them in sectors such as oil and gas, civil nuclear, and aerospace, having a trusted architecture to guide the implementation and security of the systems involved is really, really important, because we've seen operational technology and information technology converge in recent years. So in this talk, I'm going to give a broad overview of what industrial control systems are and what makes them special. We'll look at the devices which are typically found in these systems, what their purpose is, and what security for them looks like. We're then going to talk about what the future of ICS looks like with Industry 4.0 and how Industrial Internet of Things technology is revolutionizing these systems. We'll look at the Purdue Enterprise Reference Architecture, which is sort of a standard model for mapping out ICS, or at least it has been for quite some time. And we'll then have a look at what the common issues for securing ICS are, so both historically and more recent, and look at a couple of case studies. Firstly, the 2015 Black Energy 3 attack on Ukraine power grid, and also the more recent security incident at Oldsmar Water Treatment Facility in Florida. We'll use the model to map out these attacks and visualize the stages that took place. After this, we'll discuss what the issues are with the standard Purdue model in the context of modern systems, and I suppose why the strict segmentation may be inappropriate now that we have devices connected to the cloud. After this, we'll look at some of the options that have been discussed for making new architectures or adapting existing ones to Industry 4.0, and finally give a summary of these and discuss the validity of the Purdue model going forward. So let's jump right in. What are industrial control systems? Well, with industrial control systems, you might also hear terms such as operational technology, ICS, which is industrial control systems, and SCADA. But they do have different meanings. Operational technology is kind of the overarching term, and that is just, as it says on the tin, it's technology which allows people to manage industrial operations. Industrial control systems, well, these are the systems which are used to monitor and control the processes. For example, the robotic arms, manufacturing lines, safety systems, valve controls. SCADA is really the software which allows the operators to monitor the running processes and provides the access to the control functionality. Well, traditionally, you might find SCADA software installed on machines in a control room. In recent years, we've seen operational technology and ICS networks move to much larger geographical areas. So you might now have SCADA software, which is controlling devices across many, many miles in different plants. So it's not a new concept, ICS. It's been around since the 1950s, and they're always getting more complex and distributed across larger areas as years have gone on. So before we move in and talk about ICS in more detail, what are the common devices? What kind of things do people talk about when they talk about ICS? So the main thing if you have any knowledge of ICS, the main thing that people talk about are PLCs, programmable logic controllers. These are industrial computers, which they take inputs from sensors or input devices, and they just process their state and they trigger output. Quite simple. They're ruggedized, so they're designed to withstand harsher environments than standard computers. So the kind of environments you might find within industrial plants, e.g. high operating temperatures. Often these will be programmed with ladder logic or structured text. You don't need to know too much about those, but those are kind of the two standard programming languages. Similar to PLCs, we also have remote terminal units. They perform a similar functionality, but their main purpose is for communication of the process state back to the SCADA systems, with some element of control too. They're often more distributed than PLCs and may use wireless communication. That's not to say that PLCs themselves, you wouldn't find them using wireless communication, but at the same time, it's just a general trend that RTUs tend to be a bit more spread out in wireless. You might find RTUs at the top of a telephone pylon or an electric substation to allow the electricity companies to monitor the state of the process. We also have human-machine interfaces. So these are basically just screens. They can be touchscreen, they can just have buttons, and you either find them next to the process. So if you think about someone working in a plant, you'll find a screen maybe while the operator is trying to control a conveyor belt, and it shows them the status of that, and they can stop it, they can see what's going on, or they can make changes to it. But you also might find HMI software running on a desktop machine in a control room alongside the SCADA software. And the SCADA software will have the HMI functionality built in, but it may also have the opportunity to allow the operators to reprogram the PLCs and issue firmware updates. So what's Industry 4.0? What is the Industrial Internet of Things? This is a good quote, I think, which kind of sums it up. And Angela Merkel said, it's the fusion of the online world and the world of industrial production. And it's all to do with processes becoming smarter. So like smartphones, smart homes, smart voice assistants, factories are now the latest area to get the smart treatment. Industry 4.0 and Industrial Internet of Things go hand in hand because it's the IoT devices that enable the greater interconnection, and data collection than traditional systems. So we have what are called cyber physical systems, which is a pretty straightforward concept. It's the blend of cyber and physical, where we would previously have had basic sensors and actuators connected to simple PLCs, which may feed their data up towards SCADA systems, custodians, and enterprise networks. We now have the data processing being done within the device itself, or near to it. And so this increased data collection, it brings with it all kinds of benefits for efficiency, such as faster batch changeovers, automatic track and trace, automated reporting, and in theory, businesses should also see reduced running costs through reduced waste, fewer quality issues, and better use of resources. The data can be fed directly into supply chain networks so as to predict stock requirements, and systems can be remotely controlled or managed. So this all sounds great, right? Well, we know that greater interconnectivity creates more attack vectors and more security challenges. Where security administrators would previously have a lockdown control network, which is air-gapped from the internet, we now have control devices connecting to internet networks. Systems that would previously have been in silos are now required to connect to each other, or at least have common connection to log storage systems. To combat this, we need to have robust security plans in place from the beginning of any IIoT implementation, rather than jumping to integrate and make use of this exciting new technology, and then think about adding on security later. Particularly with critical infrastructure, so critical infrastructure is like your oil and gas, nuclear sector. It will take some time before the infrastructure owners and the governments involved become comfortable with this technology. So we're also going to talk about the Purdue Enterprise Reference Architecture, which, like I said, is a model for mapping out the systems. And it segments the system into 6 levels, 0 to 5, each of which has its own specific purpose. This helps to isolate the control zones from the enterprise zones, and therefore reduces the risk of attacks. Level 4 and 5, these are your highest levels, and they focus on enterprise technology and systems. Common systems include web servers, mail servers, and enterprise workstations, which you might find at these levels. This is the kind of corporate level network, far removed from the plant itself. Then between levels 4 and 3, we have the demilitarized zone. So this resides between 2 firewalls and often includes remote access servers. Level 3 is your manufacturing operations, and that's where you have historians and overall monitoring systems. Level 2 is the control systems, where we'd find SCADA and HMIs. And level 1 is the PLCs and RTUs, and they are connected directly to the process, which is level 0. In some situations, you might also find this safety zone, which you can see at the bottom of the chart, and that's where the safety critical processes are. So this is where you've got systems that would automatically trigger the operation to stop, given an exact, like if the electricity went through over a threshold, or an operator pressed a reset button. These should be as separated as possible from the enterprise network, and ideally air-gapped. So that's why they're right at the bottom of the architecture. This is a bit more of an in-depth view of it and the kind of devices that you might see. You'll also see I have the firewalls situated between levels 4, the demilitarized zone, and level 3. And this is kind of a good overview of the kind of devices that you might find in each level. So why do we need to secure ICS? Well, hopefully the answer to that is pretty self-explanatory, but there are also some common issues which you get from securing ICS. And so in an ICS environment, the typical enterprise IT doesn't work. You can't just have the same cybersecurity team in charge of both your IT and your OT networks. There's a couple of common security issues with ICS. Firstly, in IT, availability isn't as so important as it is in OT. If you have downtime in OT, it can be extremely really costly and also dangerous sometimes, particularly if it's a safety system. Furthermore, a lot of the systems also have legacy systems still built in. The plants have been commissioned many, many years beforehand and will still be operating for at least, say, 20 years. For this reason, you have older operating systems running within the factory environments, such as Windows 7 or even older. It's not cost effective or even safe sometimes to upgrade or patch these systems because you don't know what it's going to do to the underlying process. Having said that, like I said, having Windows 7 and Windows XP and other commercial off-the-shelf systems involved, this is where you can get vulnerabilities in place, and if you don't patch them, then you've got a big problem, and you probably need to air-gap them as best to your ability if you're not going to patch them. I think misconfiguration is also one of the main issues. Having a lack of firewalls, or the firewalls misconfigured or routers misconfigured, would allow systems which are not normally permitted to connect to the internet being directly connected. So there's an Internet of Things search engine called Shodan, and on there is where you might find examples of industrial control systems which are being misconfigured or are connected to the internet. Now, this demand for internet connectivity has been accelerated by the pandemic in the last year. And for this reason, if corporations haven't properly thought out how they want their people working from home, you might have insecure implementations of remote access software, which we'll go into in a minute, a bit further. One of the other main issues is that many of the communication protocols used are insecure. So when I said that ICS has been around since the 1950s, there are protocols that have been around since the 70s, which have absolutely no encryption and no checking of who has sent the data and where. So if you have a PLC which uses Modbus, chances are if an attacker got into your network, they could send specially crafted Modbus packets to make the PLC do whatever it wanted, or start or stop the process. This is extremely dangerous, as you can imagine. So what does a typical ICS attack flow look like? What's the kind of chain of what attackers like to do? Well, firstly, they'll gain access to the corporate enterprise network. That's usually how these attacks go. Usually there's a vulnerability either in an enterprise system or it's part of a phishing attack against the corporate users. From there, they'll pivot around, have a look and see where they can go, extend their foothold there, and find some devices which could potentially give them access to the lower down levels. If they're able to do that, they can gain access to the control network, install malware, and disrupt the processes. So quickly, we'll look at the 2015 Black Energy attack on Ukraine's power grid. So like the previous slide, this is a top-down attack. The attackers got access to the enterprise zone, stole VPN credentials from there, and then moved downward to attack the control zones. And it ended up that 225,000 customers were without power. The HMIs were what were targeted, and they ended up modifying circuit breakers without the operator input. Post-incident analysis showed that the attack probably came from a spear phishing campaign, which meant that the corporate workstations were infected with the Black Energy 3 malware. From there, the attackers found VPN credentials, which allowed them to get into the control network. They disrupted the SCADA systems and disabled the uninterruptible power supplies, which meant that if things went wrong, which they did, everyone was without power, or 225,000 customers anyway. So here's a kind of overview of how that worked. Step one, they target the enterprise desktops. They then pivoted around, found VPN credentials on an Active Directory server, and then used that to go from their same external network to attack the remote access server. And from there, there was a misconfigured router, which allowed them access to the SCADA systems. Not all attacks have to be this sophisticated though. And in the case of the attack recently this year on the Florida Oldsmar water treatment facility, this was a very low sophistication attack and involved the use of TeamViewer. Now, you could talk for a long time about how TeamViewer is not a secure system for using remote access, particularly in corporate and industrial control systems. But in this case, yeah, that's very bad practice. There was a leak called the COMB leak, or COMB leak, in February 2021, which was 3.2 billion email password pairs, and it was described as the biggest breach of all time. 3 days later, an attacker remotely accessed a machine, which had TeamViewer installed alongside the HMI software. The attacker wasn't very sophisticated, and it seemed as if they decided to just manually change the pH levels from what would be a normal operating level way up to something which is completely unnormal and unacceptable. Now, luckily, one of the operators that was working there spotted it within a few hours, or at least at the end of the day, and it was quickly rectified without it affecting any customers. Now, it's quite possible that the reason that TeamViewer was on this system is because of a bad response to the working from home situation with the pandemic. And if you don't think about how remote access will work before just installing things, then you're going to have some poor implementations. So, like I said, it's very low sophistication. Not all attacks have to come from the highest levels and go all the way down. If it's misconfigured enough, you can get direct access to the control networks. Now, luckily, no one was injured in this attack, but if the attacker had been more sophisticated, maybe they would have been able to hide their actions better, and we might not have known about this until it was too late. So we've talked about the Purdue model, and we've talked about Industry 4.0. So there is one main issue with using the Purdue model and its segmentation for Industry 4.0 and Industrial Internet of Things. And it's the Industry 4.0 has this reliance on interconnectivity and sensors connecting from the internet networks at the top directly to them at the sensor level. So we don't have this hierarchical data flow anymore. You don't have your corporate at the top and then down each level to the control network, and then the control network not being able to access the internet, at least without having to go through all the different layers. So there's more opportunities for attack if you're going to have this lack of separation. The data that's gathered and processed at level 1 and level 0, sent directly to the cloud, it bypasses the logical hierarchy of the Purdue model. And even if you were to make some sort of system where you wanted your devices at level 0 to send data up to the cloud through the corporate network, the amount of overheads and the amount of time that this would take adding on would really decrease your efficiency and might actually increase opportunities for exposure. So this is a kind of simplified overview of the two different models. We have the Purdue model on the left, and we have the IoT cloud model on the right. It's a very simplified version, but essentially we have both the cloud and the edge networks, and everything that's in the edge will connect through an edge gateway to the cloud. So in that case, is Purdue still relevant? If you're not going to have this strict segmentation between each level of the network, what happens? Well, as the architectures bypass traditional hierarchical levels, it could be said that Purdue is outdated. When we think about security, of course, the issue of OT and IT converging isn't new. And as we have seen, most incidents seem to be a result of misconfiguration. However, IoT environments, this edge gateway, which connects the cloud and the edge networks, would be the most critical component to secure. And surely a breach of this could be catastrophic, particularly if a business has opted to use IoT devices for safety critical applications. So we move away from the Purdue model, then what happens? Well, we might be presented with more concerns. Because the model is so successful, the level of trust the enterprises have given it is demonstrated by the success. And many businesses may be reluctant to design their networks on new and untested architectures. Purdue is referenced within so many standards, at least the main standards for ICS security, such as the NIST 882 standard, which has long been the go-to standard for IT and OT systems. So if we move away from these trusted architectures, we need to give even more thought to cybersecurity in case there's any misconfiguration. And this will also take time to move between Industry 4.0 and IIoT. The vast majority of traditional control systems in use today will not be decommissioned or radically altered for many years. So if enterprises are looking to integrate IIoT, then some experts have suggested instead of scrapping the Purdue model, we should create a hybrid approach and have an edge computing layer somewhere between layers 2 and layer 3. So how do we adapt the Purdue model? Can we adapt it? Well, yes, one of the most promising models is from the European Union Agency for Cybersecurity, and that retains a 6-level approach for the Purdue model. We see the IIoT platform, or edge gateway, situated at level 3, alongside traditional systems such as a historian. Level 5 in this instance has been replaced with a cloud layer and includes external cloud services, as well as bidirectional communication with the sensors and actuators from the IoT platform. Of course, in this model, you can't see the firewalls which were present in the Purdue model or the traditional Purdue model, but there will still be firewalls between each of the layers. The whole document, which it features in, is called Good Practices for Security of Internet of Things by the European Union Agency for Cybersecurity. and it's probably more beneficial for Industry 4.0 than past models, and it's much more relevant than some of the older standards. I really recommend reading this practices document if you're interested in further implementation specifics. Other proposals for security, if we move away from strict segmentation, we need zero trust. So like I said with Modbus and the protocols, if there was implicit trust by default when ICS were first made networked. And this is obviously bad practice in the modern age because nobody back then was thinking about cybersecurity. But for now, we need the devices to be hardened by default and not trust in each other unless it's absolutely necessary. We also have next generation firewalls, which would provide enhanced logging and threat detection. These are able to communicate with asset management systems and use deep packet inspection to monitor and provide businesses with an overview of the assets which are within their networks. They also provide information about vulnerabilities from these assets. The data from this can be fed into security tools, such as Palo Alto Networks IoT Security, Azure Defender for IoT, and the Dragos platform. And a lot of these use anomalous traffic detection using machine learning. So there's some creative ways we can go about moving away from Purdue, or at least segmentation for IoT devices. So what's the conclusion of this? Is the Purdue still relevant? So increasingly, cyber attacks are having more physical effects and becoming more dangerous. Experts are warning that it's a matter of when, rather than if, a cyber attack kills someone. So in the last year, a German hospital was hit with a ransomware attack, which was kind of the first indirect cyber attack or death from a cyber attack, as the A&E patient had to be diverted to another hospital and died en route. This is indirect, of course, but as we see more convergence between OT and IT, expect to see more attacks and possibly direct deaths as a result of incidents in the near future. In the case of the Oldsmar water treatment facility, if the attack was more sophisticated, then it could have been catastrophic. But as we've seen from the attacks, it's not so much the architecture that can be at fault. A lot of the time it's the misconfiguration by humans or having security as an afterthought, which has long been a common issue. That being said, although the architecture is not also at fault most of the time, having an up-to-date architecture will allow administrators and designers to follow and help to ensure the system's secure from the outset. Purdue is definitely still relevant, considering that most industries will take some time to move beyond their current setups and integrate industrial Internet of Things. But at the same time, we know that Purdue model isn't entirely applicable for these modern systems, which don't have direct segmentation. So architectures such as the European Union Agency for Cybersecurity model should at least be considered, even if businesses do not have IoT technology in their plans for the future. Looking at these new architectures will enable the businesses to stay protected and also prepare for Industry 4.0. And that's the end of the talk. Thank you very much for listening, and thank you for inviting me here. It's been a pleasure.
It's been a pleasure having you. So I've had a question for you. Specifically, when you deal with these models and you have recommendations from the NISA, right?
Mm-hmm.
So at least in the world of IoT, specifically, so they have this baseline set of recommendations for IoT, and literally no one applies almost half of them.
Mm-hmm.
So is this something you fear is going to have a similar effect with the revised Purdue model?
Yeah, I think so. It's one of these things you can't force people to comply with these standards. You can't. If people are going to misconfigure systems, then they will. And I think a lot of the issue with misconfiguration also comes from a lack of funding. So when they were talking about the Oldsmar water plan, in the court case, it was noted that there was a lack of funding for cybersecurity, which was one of the issues. So if people aren't going to deal with them, then how can we stop the attacks? Well, if we have some of the tools which I mentioned, like the Palo Alto Networks offering and Azure Defender, these can provide recommendations to businesses if they have them installed without them having to go and get external analysts to come in. So at a very low level, they can say to you, you have these devices which have these vulnerabilities. And trying to make things more intelligent and make things easier for security owners or owners of the systems who are in charge of the security will definitely help to do things. So using these new tools, I think, is the main thing in trying to make use of the technology.
Alrighty, awesome. And since IoT devices require certain levels of speed, how much does that compromise the security of these systems? How can these systems use encryption as well as be efficient enough for optimal use?
Yeah, that is one of the issues. Like if you have encrypted traffic, decrypting it and encrypting it can provide some overheads. It's not a simple answer in terms of what we can actually do to make things smart, but it doesn't have to be, speed versus security. I think businesses can compromise somewhere in the middle, particularly in ensuring that devices have the robust vulnerability detection on all of their devices. It's a good question, and it's not one that has an easy answer, I'm afraid, but I'm sure that businesses would like to find some sort of compromise when they're doing their planning.
Mm-hmm. And do you think a hybrid approach is the best? What's your personal opinion on the Purdue model?
So personally, I think it is a bit outdated, and because this is new technology, we haven't really seen most of the attacks that we've seen anyway for OT networks have come from traditional devices. So we haven't seen a lot of high profile, at least, security incidents for IoT devices and industrial control systems. So it remains to be seen whether or not the Purdue model is beneficial, but we're not going to know unless we try these new architectures. And having said that, there are other architectures for IoT devices in industry, but they don't really talk about industrial controls like the traditional systems. Mm-hmm. So they're perhaps not as applicable for these large enterprises which are just looking to transform their business. And maybe for smaller enterprises, they're more applicable for people that are designing a whole plant afresh. So it's kind of a trade-off, and we have to see in the years to come how these architectures cope and if we need to refine them.
Awesome. Thank you so much.
Thank you. It's been great. And a lot of fun.
Yeah, it definitely is. And you have quite a few positive comments and good discussion going on in the YouTube comments. So thank you so much for being here today. And that was fantastic. And I really enjoyed your presentation.
Thank you. Thank you. It was great. Thanks for the opportunity, guys. Thank you to the whole team.